Good morning, everyone. I'll be discussing today the article Historical Perspective of Finger Joint Motion, the hands me downs of our predecessors. It is actually an exhaustive 25-page article by Ronald Linscheid, which was published in Journal of Hand Surgery American volume in 2002. It is actually a Richard Smith Memorial Lecture. The article begins with paying tributes to Sir Richard Smith, who had immense interest in knowing the mechanics of finger motion. He has also written all his study and important points in balance and kinetics of fingers under normal and pathological conditions. The interest in mechanics of finger joint motion was much more during the late 20th century, the reasons being the inauguration of various hand surgical societies across the world, much more improved knowledge on physical anthropology, resurgent interest in rheumatoid arthritis, the innovation of functional electromyography, and seminars directed at specific topics. The concept of physiological cross sectional area of a muscle was first given by Rudolf Fick in 1900, and he said by making various cross sectional cuts on a muscle, the maximum cross sectional area of a cut muscle was called as a physiological cross sectional area of that muscle. And he calculated the force by the product of this PCSA with 3.6 kg per centimeter square. The drawback of this force measurement was that it did not fit on any rigid body and static equilibrium. To overcome this drawback, Paul Brand measured the resting length of a cut muscle. What he did was he cut the tendon at the musculotendinous junction and at the insertion and turned around so that the muscle will get a paralleloid or a trapezoid shape, and then that resting muscle length was measured intramuscularly, and then the force was calculated by taking the ratio of the muscle volume to that fiber length which was measured. If you trace back way back in 1667, Nicholas Steno has also given the similar concept was what Paul Brand has told, and he has also measured the cross-sectional area approximately of any functioning muscles was 22.5 newtons per centimeter square. The article talks about various contents under these headings like mechanics of movement, PIP equilibrium, MCP equilibrium, EMG, extensor aponeurosis, the basic pathology in rheumatoid arthritis, and also the collateral ligaments at the MCP joint. In the mechanics of finger movement, most of the studies were done by Littler in 1973, and he attributed the hand with its natural forms to Fibonacci series. He said that when a finger is completely flexed from completely extended position to completely flexed position, the fingertip usually approximates and it takes a spiral equiangular spiral curve which is equal to the mathematical curvature based on the converging sequence of ratios of approximately 1.6. So same is depicted in this picture of Fibonacci sequence. When the finger is completely extended and when it flexes, the tip takes a spatial configuration and fingertip progressively takes an equiangular spiral. In the Highland View Conference of Hand Function in 1965, Napier presented his concept on hand grasp for the first time in 1965, and he divided the hand grasp into two types, the power grip and the precision grip. And he said because of this function of the hand, the entire prehensile activity of human hand is based. He has divided the power grip into 4 stages, that is, opening of the hand, then positioning of the fingers around the object, approaching the object, and grasping the object by digit and palms. And he has explained all these 4 stages in various mechanics. For opening of the hand, it is important that there is a simultaneous but contraangular movement of MCP and IP joints. And he also said that if you flex the wrist initially in the resting position itself will isotonically stretch the EDC tendons and relaxes the profundus, which will help in opening the hand. To position the finger, it is determined by the degree of how much the MCP is extended when you're opening the hand, and the IP curvature, which is adjusted through the wing tendons. The wing tendons are nothing but the lumbricals and the palmar interossei. To approach the object, the MCP angulation is modified and adjusted by the phalangeal insertion of the interossei to regulate the abduction and rotation of the proximal phalanges. Especially if you try to approach an object and try to hold, the ulnar fingers try to rotate more. And finally, to grasp the object, the FDPs have to work because the fingers have to flex along with the dorsal interossei, and the tenodesis of wrist extension is required. Long and Landsmeer has also told that whenever you power grip an object, the external force has to be balanced by the point contact of the object with the fingers inside. And to do that, you require an isometric contraction of the muscles. But for the precision grip, which is also called as precision handling, the manipulation of the object is between the fingers and the thumb pulps only, not the palm. Here, initially the thumb has to oppose and abduct at the first CMC joint and the MCP joint and try to hold the object, and then it can be translated or rotated between the digits. Here the muscles has to act isotonically. The length remains same, but the tone remains the same. Landsmeer gave the concept of precision handling, and he said that the motion of the MCP and IP joints require the joints have the ability to regulate reciprocally. Reciprocally means they have to act in coordination. And he has given a mathematical formulas to calculate this joint motion. He applied the moment equations to predict the mechanical behavior of the linked system in the human finger. That is, if you have biarticulate joints like MCP and the PIP joint, the intermediate bone, which is the proximal phalanx, usually tends to collapse. If you see in this picture, because of there is no insertion of either the flexor or extensor on the PPX, it tends to collapse. So if the moment arm of the extensor tendon is increased, then the PPX tend to go dorsally. If the moment arm of the flexor side is increased, the PPX tend to go volarly. So in the normal finger, the movements of PIP and DIP joints are usually coupled. So they are linked mechanically with respect to the angulation occur in the same direction, not in the opposite direction. The motion between the PIP and DIP is coupled because of the unique composition of this extensor apparatus. And the coordinating mechanism has two components, both of which depend on the mechanical construct being loaded by the tension in the FDP. So these two components are nothing but the static component and the dynamic component. If you see the static component, it is given by the oblique retinacular ligament, which crosses volarly from the PIP joint and inserts on the extensor aspect crossing the DIP joint. So when you flex the DIP joint, the oblique retinaculum ligament tenses, and then it approximates more towards the center of rotation of the PIP joint. Though it crosses the PIP joint volarly, because of the DIP being flexed and it going more towards the center of rotation, it has very minimal effect on the flexion of the PIP joint. That is why it is a static component of the PIP equilibrium. Whereas the dynamic component of the PIP equilibrium is by the extensor apparatus, which consists of lateral bands and the central slip. Now, if you try to flex the DIP joint, the lateral bands go more dorsally and the moment arm of the extensor side increases. When this happens, the lateral bands move distally and the tension in the central slip reduces. Because of this, and you continue to flex the finger, and when the PIP starts flexing, the lateral bands again tend to move towards anteriorly, and move towards the center of rotation of the PIP joint. And then the momentum of the extensor tendon again tends to decrease and comes more towards the flexor momentum. So this movement continues till the momentum becomes equal. So that is why these are the dynamic component of the PIP joint equilibrium. The moment the lateral bands move towards the anterior side, the tension in the central slip increases and then it takes over the rest of the momentum. So similarly, the extensor tendon excursion across the metacarpal till the DIP joint was nicely depicted in structural and dynamic basis of hand surgery by Zancoli. He measured the excursion of the extensor tendons and said that the excursion is nearly necessary of 24 mm, wherein 14 mm is by MCP joint, 6 mm at PIP and 4 mm at the DIP joint. But if you carefully see back this diagram of Zancoli, here the total excursion is stored as only 20 mm instead of 24 mm. That is because the descent of this lateral band at the PIP joint saves approximately 4 mm of excursion. Now, if you see the MCP joint equilibrium, it mostly depends on the intermediate component, that is the proximal phalanx, which is also called as intercalated segment. As we discussed earlier, the direction of the angulation of this PPX is determined by the relative beam lengths of the flexion and the extension respectively at MCP and PIP joints. So Landsmeer said that if the tendons cannot be loaded simultaneously, which is very obvious because when you are trying to hold an object, your flexors are acting but your extensors are not. When you try to release the hand, your extensors are acting but not the flexors. But he says that if the tendons cannot be loaded simultaneously, then the joints can never reach equilibrium without the intervention of lumbricals. So that is why the importance of lumbricals are intra-ossei in our finger mechanics. It acts as a third component and maintains balance throughout the movements of the fingers, whether it is flexion or extension. So the same has been depicted with various formulas. And interestingly, they have found that FDS is not normally activated until you grasp the object very firmly. If you just try to hold an object or just try to hold a cup or a bottle, only your FDP acts. But if you try to hold the same bottle tightly, then the FDS comes into picture. Another way where FDS gets into picture is when you flex the wrist, the FDS acts much better. So therefore, in regard to the finger ruled by the extensor tendon and both flexors, we can state that the equilibrium of all three joints is not possible unless the intrinsics come into picture. Next thing they saw is electromyographically they tried to analyze that during which movement of the fingers which group of muscles are acting. And they found that if the hand is at the rest, then the finger position usually depends on wrist position, not on the muscles. Because if your wrist is in flexion, your fingers goes into extension. And if your wrist is in extension, because of the tenodesis effect, the fingers go into flexion. They found during the active finger flexion, FDP is the one which is most commonly acting. But at the same time, when you flex the fingers with wrist flex, then it is FDS which takes over. Similarly, during only MCP extension, the EDC acts throughout the motion and the lumbricals act throughout the IP extension. So if you see, the contracting lumbricals usually reduce the tension in the distal FDP. And if we say that lumbricals contract means the MCP has to flex and the IP has to extend. This is because the FDPs give origin to the lumbricals and these lumbricals go volar to the transverse metacarpal ligaments. And that is why it maintains the ability to modify the tension between the FDP and the extensors in all position of the fingers. Coming to the extensor aponeurosis, as we all know, the basic anatomy of the extensor apparatus and the aponeurosis, if you see, it is a unique complex of interlacing fibers from the extensor tendon, wing tendons and the fascial attachments. Wing tendons I have already told is palmar interossei and lumbricals, and various facial attachments. Facial attachments are nothing but the sagittal bands, the triangular ligaments, and the oblique and transverse retinacular ligaments. Remarkably, the ability of the extensor assemblage to modulate the tensions within the interlacing fiber bundle is the key to useful finger movement. The sagittal bands usually anchor the extensor tendons over to the dorsum of the joint, and they also limit the bow-stinging tendency of the extensor in hyperextension of the MCP joint. Another concept is force nucleus, told by Zancoli himself. We'll be discussing in subsequent slides. The importance of collateral ligaments in MCP joint is also immense. We all know that there are radial and ulnar collateral ligaments, but anatomically they are not positioned similarly. Radial collateral ligament is actually angled more dorsal and palmarly, more obliquely than the corresponding ulnar collateral ligaments. Also, the angulation of the collateral ligaments also decreased if you see from the radial side fingers to the ulnar side fingers. And the contact area between the metacarpal head and the base of the phalanx in extension is completely centralized contact. As the finger flexes, the contact becomes more lateral. So when the contact becomes more lateral, there is tendency for it to sublux proximally. And this unique arrangement of the collateral ligaments prevents this subluxation while flexion of the MCP joint. And also because of this attachment, when you try to do a ulnar and radial deviation of the fingers usually go into ulnar deviation and the proximal phalanx supinates. This is commonly seen in the ulnar sided digits, which is the ring finger and the little finger, and this helps in grasping a spherical objects much better way. So how is this mechanics help us to analyze the deformities in rheumatoid arthritis? So the authors say, because of the article, the role of finger flexion in rheumatoid deformities in MCP joint by E.M. Smith and colleagues is the basis of this deformities in rheumatoid arthritis. They have studied that whenever the MCP is flexed in 30 degrees, there are three forces which are acting on the MCP joint, which are the deforming forces. Usually it is the palmar subluxation force is almost 3 times the output force. Then the flexion tension to maintain the stability is around 6 times. And the compressive force is almost 7 times the output force. So whenever the MCP is flexed in 30 degrees, the tendency to palmar subluxate is 3 times the extensor force. Another thing, if you see, most of our flexor tendons come from the ulnar side. So if you see the flexor tendons of the index, middle and ring fingers, usually try to boasting ulnarly in their passage into the flexor tendon sheath by 15, 7 and 3 degrees respectively. So this also acts as a deforming force for the fingers to go into ulnar deviation. So these ulnarly directed forces from the thumb and also the anatomical features of the MCP joint helps us to explain this development of ulno-palmar deformities in the MCP joint in rheumatoid arthritis. So here in this picture, if you can see, this flexor tendons come from the ulnar side and goes into the radial fingers. There is always a tendency for it to sublux towards the ulnar side. So usually before the concept of this flexor tendon bowstringing, most of the surgeons usually used to relocate the ulnarly subluxed extensor tendons by placating the radial sided collateral ligament, and then the deformities usually were recurring because the original pathology is because of the flexor tendon bowstringing, which is tough to treat today till date. So as I was telling, the force nucleus concept by Zancoli, which is the common attachment of the extensor tendon, the sagittal band, the lumbricals, and the transverse intermetacarpal ligaments. So what they have found is, whenever the MCP joints are at rest, and if you take a cross section and then you flex the MCP joint and take the cross section of the metacarpals, The ulnar digits, which is little and ring finger, usually move in according to the middle finger. So they make a right angle triangle. As you can see in this picture, as the fingers try to flex, the little and ring finger metacarpal heads go down at an angle of 90 degrees to the middle finger. So this will try to stretch the intermetacarpal ligaments. When you're trying to hold the object straight, the intermetacarpal ligaments stretch, which is also a deforming force for the fingers to go towards the ulnar side. Another deforming force is also the abductor digitae minimi muscle, which they have found can also be contributed to this deformity in the rheumatoid arthritis. Thank you.